This video is on magnetic induction. Question number 1. Define induction and induce. From dictionary.com, induction is the process by which electrical or magnetic properties are transferred without physical contact from one circuit or body to another. Induce means to produce an electrical current by induction. So compare this definition, induction and induce, to action at a distance forces like Newton's law of gravitation and Coulomb's law and the magnetic force. These forces exist even when two objects are not in contact or do not touch each other. Question number 2. What are the units of electromotive force, E? This is the Greek letter eta. It's volts, which is joules over coulombs. Question number 3, true or false? Electromotive force E is a force. It's false. It's just a bad name. Question number 4, define flux. Draw a picture. So from dictionary.com, flux is the presence of a field of force in a region of space represented as a set of lines indicating the direction of the force. The density of the lines indicates the strength of the force. Lines used to represent magnetic fields in depictions of magnets, for example, follow the lines of flux of the field. See also magnetic flux. So this image on the top left, it's like we have a wire. That's the rectangle, a closed loop. And now we have these 3 lines that go through that closed loop. So the more lines that go through that closed loop, the greater the flux. Look at this image on the top right. These 3 X's mean into the page. So we have a closed loop of wire. It's a magnetic loop. And we have 3 lines that go through that loop into the page, which is the X with the circle. Now look at the image on the top right. We got the dot and a circle. Now we have 3 lines going out of the page. So we have this closed loop. It's like a rectangular metal wire loop. And we have 3 lines going out. So now we have a north pole and a south pole. And magnetic field lines always go from north pole to south pole. So in this image, we have magnetic field lines going from left to right. We have 3 magnetic field lines in this image. Do you see this loop in the middle? Imagine this loop rotating, okay? So sometimes you could have 3 lines of flux going through that loop. And when this loop rotates, sometimes we could have 0 lines of magnetic flux going through this loop. Okay, so this question was asking, define flux. We could have flux of electric field lines, flux of gravitational field lines, and flux of magnetic field lines. Question number 5. Magnetic flux is defined as phi equals BA cosine theta. Define and give the units of each variable. Draw an image showing magnetic flux and label theta in the image. Also draw an image of magnetic flux when theta is 0 and when theta is 90 degrees. So let's take a look at this equation. Phi equals BA cosine theta. B is the magnitude of magnetic field going through the loop, has units of Tesla. A is the area of the closed loop, has units of meters squared. Theta is the angle between B and A, has units of degrees. And phi is the magnetic flux, has units of Tesla times meter squared, which is also called a Weber, WB. So if theta is 0, then cosine of 0 is 1, so the magnetic flux phi is a maximum. This means that the magnetic field lines in the closed loop are perpendicular to each other. Okay? It's quite difficult to draw this on a 2D paper. Okay? Now, if theta equals 90 degrees, then cosine of 90 is 0, so the magnetic flux is minimum. This means that the magnetic field lines and the closed loops are parallel to each other. Okay? So, once again, if theta is 0, that means the magnetic field lines are perpendicular to the paper. If theta is 90, that means that the magnetic field lines are parallel to the paper. And if it's parallel to the paper, there's no magnetic field lines that go through the paper. Question number 6. Consider a single loop of wire which is 25 centimeters by 25 centimeters. So, passing through this loop is a magnetic field which has a magnitude of 0.220 Tesla. Part A, assuming that the magnetic field is parallel to the normal of the loop, what would be the total magnetic flux passing through the loop? Well, it says parallel to the normal of the loop, so that's when we know that theta is 0. So for part A, we were given B and A. Now we have to decide that cosine, or we have to determine that theta is 0 degrees. Part B, assuming that the magnetic field meets the normal to the loop at an angle of 35 degrees, what will be the total magnetic flux passing through the loop? Okay, theta is 35 degrees. Part C, assuming that the magnetic field is perpendicular to the normal of the loop, what will be the total magnetic flux passing through the loop? Well, now theta is 90 degrees. So 0 magnetic flux passes through this loop. Question 7. Use the words to define and describe Faraday's law. E equals minus n d phi dt. Draw a picture if you have to. So this is important. Please memorize this. A change in magnetic flux through a closed loop will induce an EMF. So recall that the equation for magnetic flux is phi equals Ba cosine theta. Now we have the following equation. So this is the full equation, okay? EMF equals minus n d phi dt. Phi is Ba cosine theta. So if B changes, or A changes, or theta changes, then we're going to get an EMF. And if we get an EMF, then we're going to get a current going through the loop. Okay. So this means that to induce an EMF, we can change either B, the magnitude of the magnetic field passing through the loop, A, the area of the loop, or theta, the angle between the magnetic field lines and the loop. Okay. So take a look at the figure below. The metal coil or loop between the magnetic field is rotating. Okay. That's this loop in the middle here. According to the equation phi equals Ba cosine theta, the magnetic flux through the coil varies between minus Ba to positive Ba. Since the ranges of values of cosine theta are between minus 1 and positive 1. The faster the coil / loop rotates, the greater the induced EMF. So if the magnetic flux is 0, then the EMF is maximum. And if the magnetic flux is maximum, then the EMF is 0. So write this equation down and think about what E is going to be if theta is 0 degrees, 45 degrees, and 90 degrees. Question number 8. Consider a single loop of wire which encloses an area of 50 centimeters squared. A magnetic field which is parallel to the normal of this loop initially has an intensity of 0.22 Tesla. 220 Tesla. Over a time period of 0.2 seconds, the magnetic field strength drops to 0. Okay, so they gave us time. Part A, what will be the resulting EMF in the loop? Okay, So we have this equation, EMF equals minus NA cosine theta times delta B over delta T. Why do we have delta B over delta T? Because if you read the question, A is constant, okay? So we could substitute in the numbers for A. We're going to convert centimeters to meters. And we know what delta B is. It's 0.220 Tesla minus 0 Tesla. How do we know? Read the problem. Divided by 0.200 seconds. Okay, so we get a value. Part B, what would be the EMF in the circuit if the loop consists of 1,000 turns rather than a single turn? So now that little n equal 1,000. Okay. So we get 1,000 times the voltage in part B as compared to part A. Question 9. Consider a coil of wire which has 1,200 turns, encloses an area of 18 centimeters squared. It contains a magnetic field of 3.5 Tesla oriented parallel to the normal to the loop. What will be the induced EMF in this coil if the magnetic field drops to 0 in 0.0167 seconds? So we get the same equation as the previous problem. E equals minus n d phi dt. Substitute for phi, it's BA cosine theta. Take out the constants. A is a constant. Okay? Theta is 0 degrees. Cosine of 0 is 1. So now we have this equation that I just highlighted. Plug in the numbers and convert centimeters to meters. Question 10. The negative sign in Faraday's law is known as Lenz's law. What does it mean? So the negative sign is very important. From Faraday's law, there will be a current induced in the coil if there is a change in magnetic flux. The magnetic field of the current will oppose a change in magnetic flux. So Lenz's law states that the direction of an induced EMF opposes the change which produces it. Lenz's law is an application of the law of conservation of energy. Question 11. Use Lenz's law and the right-hand rule to determine the direction of the induced current on the metal conducting wire. So this is very important. There's only a finite number of examples for Lenz's law. So I gave you all the examples that you will encounter, hopefully. Part A, there is a magnetic field which points into the page. Okay, so imagine all of these X's are lines that go into the page. Okay. So horizontally, you have 1, 2, 3, 4, 5, 6, 7, 8 X's. Vertically, you have 1, 2, 3, 4, 5, 6 X's. So 8 times 6 is 48. So imagine we have 48 lines that go into the page. If the magnitude of the magnetic field is decreasing, then we're going to have less magnetic field into the page. We don't want to change, so we want more magnetic field into the page. So let's put our thumb into the page and our fingers, they curl clockwise. So since our thumb is into the page and our fingers are clockwise, that means the induced current is clockwise. Okay, so we're using our right hand. Take out your right hand and let's do this. Okay. Part B. If there's no change in magnetic field, then there's going to be no induced currents. Okay, so remember that equation. Write it down. E equals minus d phi over dt. And phi is BA cosine theta. So if B is not changing and A is not changing and theta is not changing, then there's no EMF. And if there's no EMF, there's no current going through this metal loop. Part C. the magnetic field is increasing. So these lines going into the page, imagine now there's more lines going into the page, going through this closed loop. We don't want to change what we're doing. So we have to put our right hand, our thumb from our right hand out of the page. Now, if our thumb from our right hand is out of the page, our fingers are curling to the left. And since our fingers go to the left, that means it's counterclockwise. So the current is counterclockwise. So we're using our right hand and we're just trying to oppose the change in flux. Part B, there is a magnetic field which points out of the page. Okay, so all of these dots with the circle around it, these are lines that go out of the page. So the arrow points out. So if the magnitude of the magnetic field is decreasing, that means we're going to have less lines going out of the page. We don't like to change what we're doing. So let's try to put our thumb out of the page. And if our thumb points towards our nose, our fingers in our right hand, they're curling counterclockwise. So the induced current is counterclockwise. Once again, for part BII, if the magnetic field is constant, if the number of lines don't change, then there's no change in flux. If there's no change in flux, there's going to be no EMF. Finally, part BIII, if the magnetic field is increasing, that means the magnetic flux is increasing. And if the magnetic flux is increasing, that means we don't want to change the amount of magnetic flux we have. So we're going to point our thumb into the page of our right hand. And you could see our fingers curl clockwise from our right hand. That's why the induced current is clockwise. Part C, there is a constant magnetic field into the page. Which direction is the induced current? So look at part I. We have like this horseshoe ring, and we have this bar, and this bar is moving to the right. So the area inside that loop is increasing. So if A is increasing, we're going to get more magnetic field going into the page. We don't want more magnetic field into the page. So our thumb is going to point out of the page. Okay. Part CII, the area of the loop is decreasing. So if the area of the loop is decreasing, that means this bar is moving to the left. So we're still getting a closed loop. We're just getting less magnetic field lines and therefore less magnetic flux. Well, we don't want to change the amount of magnetic flux we have. So we're going to want more magnetic flux. And the only way we could have that happen is if our thumb from our right hand points towards our nose out of the page. I apologize. The area of the thumb is decreasing. So we want to increase the amount of magnetic flux we have. So the way we do that is we put our thumb into the page. And our fingers curl clockwise. Part D, there is a constant magnetic field out of the page. So if the area of the loop is increasing, that means this loop in part I, it's going to have more magnetic flux. Well, we don't want more magnetic flux. So we're going to put our thumb into the page and our fingers point clockwise from our right hand. Remember, it's called the right hand rule, so use your right hand. Part II, the area of the loop is decreasing. Well, if these magnetic field lines are pointing out of the page and the area of the loop is decreasing, then we want our thumb to also point out of the page because we don't want to change the flux. So our thumb points out of the page, so the induced current is counterclockwise. Part E, a magnet is falling down and entering a loop. Which direction is the induced current if we are looking downwards? So your eyes are looking down and you see that loop. And in this picture, for part I, V means velocity. The North Pole is down, the South Pole is up. So, you know the magnetic field lines go from north to south, yeah? You could draw magnetic field lines in part I. They point from north to south. So, the thumb is going to point up. So, the induced current is counterclockwise for part I. So, in part I, as this magnet falls down, there's going to be more magnetic field lines going through that loop on the bottom. So we don't want more magnetic field lines. We want the same number of magnetic field lines. So we got to oppose that increase in magnetic field lines, so our thumb is going to point up. Part II, the South Pole is facing downwards. So for part II, once again, draw magnetic field lines. Okay? And as this bar goes down, you're going to have the opposite answer of part I. Okay? So the thumb points down, so the induced current is clockwise. Okay? So use your right hand. You notice for part A and B, the answers are the opposite. So for part A, we get clockwise, no current, counterclockwise. For part B, it's counterclockwise, no current, clockwise. For part C, we get counterclockwise, clockwise. And then for part D, we get clockwise, counterclockwise. So part E, our answer is counterclockwise, clockwise. Now, could you guess what part E is could you guess what part F is going to look like? In part F, the magnet already goes past the loop. Okay? A magnet is falling down and leaving a loop. Which direction is the induced current if we are looking downwards? In part I, it says the North Pole is facing upwards. So if the North Pole is facing upwards, as this bar magnet goes down, we're going to get less magnetic flux through this loop. So you could draw the magnetic flux, the magnetic field lines that go from North Pole to South Pole. And you'll notice as this bar goes down, we're going to get less magnetic field lines. So we're going to want to point our thumb up for part I. Now, for part II, the South Pole is facing upwards. So once again, for part II, draw the magnetic field lines. Okay? So as this bar goes down, you're going to get the opposite answer as I. So once again, for part E, you're going to get counterclockwise, clockwise. For part F, you're going to get the opposite. Sorry. Yeah, you're going to get the opposite. I is going to be counterclockwise, clockwise. Part G, there is a current carrying straight wire. So imagine this. this image on the left. You have a loop here. It's not connected to a battery, okay? There is a circular wire next to it, okay? So if the current in this wire on the left is decreasing, then what happens? Okay, so you have to do this because you got to visualize what's happening. Place your right thumb in the direction of the current. So your thumb points up. To the right of the wire, the magnetic field points into the page because your fingers point into the page. Okay. If the current in the wire is decreasing, then we need more magnetic fields into the page on the right-hand side. So our thumb points into the page in the middle of the circular loop, so the induced current is clockwise because our thumb points into the page. Part II, you understand why there's no induced current because of the equation phi equals minus n, E equals minus n d phi dt. And phi is BA cosine theta. So if B doesn't change, if A doesn't change, if cosine theta doesn't change, we're going to get no induced current. Now look at part III. If this current in this straight wire is increasing, then put your right hand thumb in the same direction as the current. Your fingers, they go into the page on the right hand side of the loop. On the right hand side of the wire, the vertical wire. Since the magnetic flux is increasing, we want to decrease that. So our thumb is going to point out of the page. So the middle of the circular loop has a thumb that points out of the page, so the induced current is counterclockwise. Okay. So in this problem, the current points upwards. Okay. In this problem, now we're going to be able to move the loop up, down, left, right. Part H, there is a current carrying straight wire. There is a circular wire next to it. The circular wire moves up parallel to the wire. So if this loop goes up parallel to the wire, the magnetic flux doesn't change, so there's no induced current. Okay? Part II, if this loop moves down parallel to the wire, once again, the magnetic flux remains constant. So remember how to draw the magnetic flux. Take your right thumb, put it in the same direction of the wire. Your fingers in your right hand go into the page to the right side and out of the page on the left side. Because remember, magnetic field lines always loop. Okay, part III. This loop moves to the left perpendicular to the wire. So there will be more magnetic field lines going into the page because we're going closer to the wire. Our thumb will point out of the page. And using our right hand, if our thumb points out of the page, the fingers are counterclockwise. Because we want to resist change. Okay? Part IV. The loop moves to the right perpendicular to the wire. So if this loop moves to the right perpendicular to the wire, we're going to get less magnetic field lines. Because most of the magnetic field lines are close to the wire. We're going to get less magnetic field lines when we're far away from this wire. So we don't want to change the number of magnetic field lines. So our thumb will point into the page from our right hand. And the induced current will be clockwise. Because our fingers from our right hand curl clockwise. Part I, a small loop of wire is inside a larger loop of wire. The larger loop of wire has a constant current clockwise. What is the direction of the induced current of the smaller loop if the current of the larger loop is decreasing? So let's imagine what's happening here. Take out your right hand, put your thumb from your right hand in the same direction of this current. You could see your fingers in your right hand go into the page inside the loop. And your fingers go out of the page when you're outside the loop. Okay? And the number of into the pages have to equal to the number of out of the pages, because the magnetic field lines, they loop around. So if the current from the larger loop is decreasing, we don't want that to happen. We want the same amount of magnetic field lines. So we're going to have to increase the magnetic field lines, or the magnetic flux. So our thumb will be into the page. Okay? So place your right thumb in the direction of the current. The magnetic field lines point into the page in the circle and out of the page outside the circle. Magnetic field lines always loop, so the number of magnetic field lines into the page is equal to the number of magnetic field lines out of the page. If the current in the outer wire is decreasing, then the number of magnetic field lines in the loop pointing into the page is also decreasing. This means that our right thumb points into the page and the induced current is clockwise, because we want to resist that change. If the current is constant, then there's no change in flux. No induced current because no change in magnetic flux. Write that down. Because no change in magnetic flux. Finally, if the current is increasing, then the magnetic field lines that are inside the loop are increasing. So we don't want that change. So we're going to put our thumb out of the page. And the induced current is therefore counterclockwise, because our fingers curl counterclockwise. Question 12. What is the phase difference between the magnetic flux and EMF in Faraday's law? So take a look at this equation. What's the phase difference? Well, it's going to be 90 degrees. Because if theta is 0, EMF is a maximum. Theta is 90, EMF is a minimum. So that's going to be 90 degrees. Question 13. What happens to a magnet if it falls down a hollow metal cylinder, and why? So take a look at this. We have this cylinder. It's empty in the middle. And this is a magnet. It's a sphere, and it's going down through this cylinder. So in a previous worksheet, we could just say mgh initial equals 1/2 mv final squared. So some of the initial GPE is converted to, all of the initial GPE is converted to kinetic energy. But now, some of the initial GPE is converted to electric current in the metal cylinder, and the remaining energy is converted to kinetic energy. So the ball slows down when it is inside the cylinder. Please do watch this video on YouTube. It's a great video. It's going to show you how this makes sense. So from kinematics, we know that all of the initial GPE becomes final kinetic energy. But when learning about flux and Faraday's law and Lenz's law, some of the energy is converted to electric current. So not all of the initial GPE gets converted to KE. Some of it is KE, some of it is current inside the cylinder. Question 14, describe the equation E equals BVL. Okay, so this is a very specific problem. The induced EMF when a straight conductor, like a metal wire or rod, moves perpendicular across a uniform magnetic field is given by the equation E equals BVL, where E is the induced EMF, B is the external magnetic field, V is the speed of the conductor, L is the length of the conductor. So you could see, here are two examples. So let's apply this equation. Two parallel rails are connected together at one end by a resistance of 20 ohms. Across these two rails, which are 45 centimeters apart, there lies a conducting metal bar. The magnetic field is uniform, has a strength of 2.20 Tesla, and is directed into the page. A force is applied to the metal bar so as to push the bar to the right with a velocity of 8.40 meters per second. What will be the resulting EMF in this current? So we're going to use the equation BVL. We were given B, we were given V, and we were given L. And I converted centimeters to meters. Okay. What would be the direction of the resulting conventional current flowing through this circuit? So remember, take out your right hand. Let's use the right hand rule. Okay. The magnetic field is into the page. So if the magnetic field is into the page, that means as this metal bar goes to the right, we're going to get more magnetic field lines, a greater magnetic flux. Well, we don't want a greater magnetic flux. We don't want to change, so we want less. So we're going to put our right thumb out of the page and our fingers curl counterclockwise. That's why the solution is counterclockwise for part B. Part C, what will be the magnitude of the resulting current? Well, BVL equals IR, because we know V equals IR, and V has the same units as EMF. Okay? So we could solve for I. Part D, at what rate is electrical energy being generated? P equals IV. Part E, how much force is being applied to this bar? P equals FV. Finally, part F, at what rate is mechanical energy being consumed? It's 3.46 watts. Why? Because that's the same as part D. And the speed of the object is constant. Question 16. A battery which has an EMF of 6 volts is inserted into a circuit. Okay. The magnetic field has an intensity of 2.20 Tesla and is directed into the paper. Okay. The resistance has a value of 20 ohms and the two parallel horizontal rails are separated by a distance of 45 centimeters. A current of 0.200 amps is measured to be flowing through the circuit. Part A, what will be the resulting velocity of the bar? So let's use Kirchhoff's loop rule. Okay. Plus V battery minus V from the resistor, V equals IR, minus V from the metal rod, is BLV. So that's equal to 0 volts, and just solve for little v, the speed. Okay. Part B, how much force is being applied to the bar, but the magnetic field as it moves through the field? Well, let's just solve for V minus IR here. Okay. So that's going to be this. And we know P equals IV. And then finally, we could use the equation P equals FV and solve for F. Question 17, draw an EMF versus time graph of a conducting loop rotating in the presence of an external magnetic field with an angular frequency of omega and 2 omega. Okay. So angular frequency, it's the number of cycles per second. So the red graph below has a frequency of F and 1 complete oscillation. The blue graph below has a frequency of 2F and 2 complete oscillations. So you could see when the angular frequency doubles, the magnitude of EMF doubles, and its period halves. Okay. If the red graph has a time period of t, then the blue graph will have a time period of t over 2. If the red graph has a maximum EMF of v, then the blue graph will have a maximum EMF of 2v. Question 18. Draw a power versus time graph of a conducting loop rotating in the presence of an external magnetic field with an angular frequency of omega and 2 omega. So take a look at the physics I did here. Okay. And remember, power is always positive. Sine squared of omega t is always going to be positive. So this whole equation for power here, we get omega squared n squared b squared a squared over r times sine squared of omega t. This is always going to be a positive number. So the blue graph below has a frequency f and 1 complete oscillation. The red graph below has a frequency of 2f and 2 complete oscillations. Okay. If the blue graph has a time period of t, then the red graph will have a time period of t over 2. If the blue graph has a maximum power of p max, then the red graph will have a maximum power of 4p max. Why is it 4? Because it's omega squared. Okay. Question 19. What is the phase difference between the current EMF and power in Faraday's law? So let's take a look at these two equations. Okay. So they're all in phase with each other because EMF has sine omega t and power has sine squared omega t. So that's in phase. Okay. Finally, question 26, define self-induction. Self-induction occurs when a change in current in a wire produces an induced EMF which opposes the change of current in the same wire. So you're not going to get any problems with self-induction in high school physics. Maybe just a definition you need to know. So an example here, we have increasing or decreasing the current in this wire will lead to self-induction. So if the current goes up in this wire, using your right hand, your thumb points up and your fingers go into the page on the right side and out of the page on the left side.